So, welcome back. Uh, we have already done the kinetic interpretation of pressure, and we found that the pressure is equal to 1/3 Nm into V square average value. Okay. Therefore, we can write this multiplying both sides by capital V, which is the volume. I'll get PV is equal to 1/3 NVM into V square, the average speed, squared speed of a molecule. So this NV becomes equal to capital N, and therefore we write, we make an adjustment. I write 2/3 N into half NV square. Okay. Of course, N is equal to NV is the number of molecules in the sample, and half MV square, this one, is the average kinetic energy. The average kinetic energy, which is translational kinetic energy of the molecules in the gas. Now, since internal energy, capital E, which is the translational part of internal energy of the system, that could have other parts other than translation. It could have rotation and vibration, etc. And we are talking about an ideal gas, then the internal energy E of the ideal gas is purely kinetic, and therefore I can write this, the internal energy, as N multiplied by half mv average square average. Okay. Now we have the equation PV is equal to nRT for the gas. So this gives us PV is equal to 2/3 E. Okay. PV is equal to 2/3 E. This relation we obtain by substituting the values, and from here now we can dare to give the interpretation of temperature in the kinetic theory of gases. What is that? It means that the average kinetic energy of the molecules is proportional to the temperature T. The average kinetic energy of the molecules, okay, how come? Because E is equal to 3/2 kb into nt, so E upon N becomes equal to half mv square, and that is 3/2 kbt, where kb is the Boltzmann constant. Okay. It means that the average kinetic energy of the molecule is proportional to the temperature. Okay. The average kinetic energy of the molecule is this, the average kinetic energy of the molecule given by E by N, and this is equal to 3/2 kbt. Kb is a constant, a universal constant, and therefore I can say that the average kinetic energy of a molecule in the interpretation of kinetic interpretation of gases, that turns out to be proportional to capital T, which is the temperature in Kelvin. Okay. The absolute scale of temperature. And we also find that this average kinetic energy, which is given over here, it is independent of the pressure, the volume, or the nature of the gas. Okay. So we find that the temperature, which is an attribute, which is a measurable quantity in the a thermodynamical quantity, a measurable thermodynamical quantity, which is a macroscopic quantity related with the thermodynamics, is related to the kinetic energy average of course, this has to be translation. Okay, so that is how we interpret the temperature for a gas, and that is nearly ideal gas with low pressure and high temperature. Okay, so next we talk about mixtures. Okay, next we talk about mixtures and the kinetic interpretation for those mixtures. After the kinetic interpretation of the pressure and also of the temperature, let us talk about mixture of non-reactive ideal gases. Okay, ideal gases. We talk about that. So we go back to the equation for the pressure, which was 1/3 of N, M and V square averaged. Okay, where we have the number of moles and the masses and the various velocities squared and an average taken, a mean taken. So I can write for the mixture of non-reactive ideal gases that this equation can be written as 1/3 of number N1 for gas number 1, M2 into V1 whole square averaged or mean value, N2, M2, V2 square mean value, etc., etc. Okay, for the various components of the non-reactive components of these ideal gases. Okay, in equilibrium, now what we find is, in equilibrium, the average kinetic energy of the molecules of different gases will be equal. Okay, whether their masses of their molecules are different and maybe the velocities are different, but the average kinetic energy of the molecules of different gases will be equal. Okay, so this is what we call an equilibrium condition. So that means that half M1 V1 square is equal to half M2 V2 square averaged is equal to, and so on, and this is given to us as 3/2 kb into T. Okay, so we get this equation, so that I can write the pressure as the number of moles N1 plus N2 plus and so on multiplied by kb into T, and this is nothing but the Dalton's law of partial pressures. Okay, the Dalton's law of partial pressures. So that is also interpreted, the Dalton's law of partial pressures is also interpreted with the equations that we obtained for the pressure. Okay, when the molecules are moving in all possible directions with all possible velocities. When I say all possible velocities, that doesn't mean that velocities are infinite, and of course they are moving incessantly without losing any kinetic energy. So that part should be borne in mind, and we have to, because the gases are ideal or near ideal, is what we are talking about. Therefore we have to consider that the pressure is low and the temperature is high. these two manifests, they have to be always borne in mind, because in the previous lecture I gave to you the isotherms and isobars, etc., which they appeared on this side of the screen, to give you an idea, and with a request that please do study these isotherms and isobars, etc., and see how much is the deviation of the theoretical values from the experimentally determined values, so that you understand that yes, if we are using the model, the ideal gas model, it is only nearly true. In fact, at various temperatures, when you have the isobars, or at various pressures, I'm sorry, yes, when on various temperatures we have the isotherms, and at various volumes we have the iso bars with the pressure is a constant. Okay, those interpretations are there. So we have been able to explain the build-up, the kinetic theory of gases for the ideal gas interpretation, to give the idea of what is the momentum exchange with the walls of the container, okay, and how this we can interpret in terms of the force which is acting there divided by the area, we get the idea of pressure, and all over that ensemble of particles which we call the gas, everywhere in the container the pressure will be the same. Of course, in arriving at these things, we have considered that dissipative effects are not taken at all. Okay, so almost the molecules are moving freely, almost the molecules are not having what we call the collisions, okay, and then these theories are interpreted. Now, for example, let's try to obtain the typical speed of molecules in a nitrogen gas at 300 Kelvin. So what we do is, we first of all calculate the mass per molecule. So this is the molecular mass for nitrogen gas, which is the diatomic molecule. So this is 28 divided by 6.02 into 10 to the power of 23, which is Avogadro's number, which turns out to be equal to 4.65 into 10 to the power of minus 23 kilograms. You can work out the calculation, you can see for yourself. And then when we make the calculations, okay, making use of this relation, okay, so V square average value, this is 3 kBT, which is equal to 516 square. We have purposely taken this value as a square value, meter per second whole square. Okay, now this V square, as I told you, is the average squared velocity, that mean of the squared velocity. And so if I take the I have this V square, this, and if I take the root over of this, we get what we call the root mean square velocity. Actually, in the root mean square velocity, we first of all in the sequence we do the S part, that is square it, then we take the mean, and thereafter we take the under root. So this I can say that therefore V square average, this is what we interpret as the square of the VRMS, root mean square. Okay, RMS, root mean square. And then if you calculate the value, this turns out to be this VRMS for the nitrogen is approximately equal to 516 meter per second at temperature of 300 Kelvin. Of course, if the temperature changes a bit here and there, and then the value of the RMS speed of the nitrogen and other gases, similar gases which constitute the air, that will be in the nearness of 500 meter per second, the velocity. And interestingly, the order of these velocities, RMS velocities, is the same as that of speed of sound in air, which varies from temperature to temperature, from humidity values, this and that, and the average value is 330 meter per second. So that's it for now. I wind up this lecture here because I have to talk about next the law of equipartition of energy. Okay, so it has been an enjoying outing, and in the next couple of outings we will finish the kinetic interpretation and the kinetic theory of gases. And I again emphasize that the set of postulates, etc., that whatever we described in this case, the same or similar will be used in the theory of metals, or in the case of the interpretation of electron, gas, etc. Okay, till then, see you.